Sometimes we need gates, some circuit to be converted into NAND gate circuit, because as I said that NAND is an universal gate. So, many logic libraries. So, when you are realizing some circuit, digital circuit, maybe only NAND gates are available. Okay. So, there are many integrated circuit chips which has got only NAND gates in them. So, if you have to realize some circuit using those chips, then you have to realize using NAND gates only. So, but normally when you do a Boolean minimization, we come up with some sum of product or product of some expression which consists of say AND and OR gates and inverters. Like for example, in this particular circuit, so ultimate expression that I have got is x equal to a bar c bar plus a bar b. Now, this a bar c bar plus a bar b, so that it means that we have got this is the OR and then these are the two AND gates. But if I do not have this AND and OR gates, so I have got only NAND gates, then you can do it like this. So, what we do, this a bar c bar, so this AND gate is converted into NAND gate. So, this is the NAND operation and this is, so this a bar b, so it was an AND gate, here we convert it into NAND gate. And after that, so there is another bubble here. So, so you can understand that this is converting this here you are getting a bar c bar whole bar. So, at this point you are getting a bar c bar whole bar, and after this inversion, so you are getting a bar c bar. Similarly, at this point you are getting a bar b, and after this bubble here, second bubble there, so you are getting, so sorry, here you are getting a bar b whole bar. So, here you are getting a bar b, and then as if this is OR, and that is a bar c bar plus a bar b. But what is this gate? Okay. So, this gate, if I say that this input is x and this input is y, so what I am realizing, sorry, this input, say instead of x and y, let us write something else. So, let us say this is p and this is q. So, what we are getting is x equal to p bar or q bar, because p is inverted here, q is inverted here, and then they are ORed. So, if you apply De Morgan's theorem, so this is nothing but p q bar. So, this gate is nothing but a NAND gate. So, you can simplify that drawing as if that this you can simplify the whole drawing like this, that this is the one NAND gate where we have got this a bar and c bar as inputs, and we have got another NAND gate where you have got this a bar and b as input, and then you have got here another NAND gate where these two are connected. Okay. So, this diagram that we have here, so this is actually for the sake of our understanding, but we must appreciate that this is equivalent to this. Okay. This is equivalent to this, which is convert. So, suppose I have got a sum of product expression, from there I have got this realization of the function in terms of AND and OR gate. So, for converting to NAND gate, what we have to do is that whatever AND gates you have here, so convert all, if there are many such AND gates, many such some product terms. So, you convert all those ANDs to NANDs, and when this and then finally convert this OR gate to a NAND gate. So, that will solve our purpose. Okay. So, I will just so in general I can say that in a sum of product expression, so f is in sum of SOP form. So, f is in SOP form, then the individual sum terms, so they were represented by these AND gates. These were the individual sum terms, they were coming there, and then it was feeding the OR gate. So, this was the situation. So, to convert to NAND, what you do is you convert each of them to NAND, and finally convert this OR gate also to a NAND. Okay. So, this way we can convert any Boolean circuit into a circuit consisting of NAND gates. Okay. So, next we will be looking into how to convert to NOR gate. Okay. So, NOR gate conversion, so you should start with the product of some expression, and then this A or B bar. So, this is ORed here, and then ultimately they were ANDed there. So, you just so this gate is nothing but another NOR gate. Okay. So, if we go by the previous explanation that we had. So, this is P and Q. So, x equal to P bar dot Q bar. So, that is nothing but P or Q whole bar. So, if you have got a product of sum realization of a set of terms, okay. So, if a Boolean function realized as a product of some expression, so you have got individual inputs there and they are ultimately feeding one AND gate. If this is the situation, then what you can do? You can replace each of these OR gates by NOR gates and then replace this AND gate by another NOR gate. So, that will give you the NOR realization of the function. So, if you start with the product of sum form and then convert it into convert the OR gates to NOR gates and then the AND gate to NOR gate, or if you have to convert to NAND gate form, you start with the sum of product expression of the function and then convert all the AND gates to NAND gates and then convert the final OR gate to NAND gate. So, they will work. So, next we will be looking in more detail this exclusive OR function, because this is very interesting function. So, XOR which is represented as this plus within a circle. So, this is also known as not equal function. Why is it not equal? So, this you see that this Boolean expression for this is x XOR y written as x bar y plus x y bar. So, whenever x and y they are not equal, output is equal to 1, okay, for the XOR gate. So, that is why it is called a not equal function. So, there are certain identities like x XOR 0 is x, x XOR 1 equal to x bar. Okay, so, we can just prove this. So, x XOR y x XOR 0, x XOR 0, if you put into this expression. So, this is x bar into 0 plus x into 0 bar. So, x bar into 0 is 0 plus x into 0 bar is 1. So, that is equal to x. So, that is equal to x. So, you have got the first identity. Similarly, x XOR 1 is equal to x bar into 1 plus x into 1 bar. So, this 1 bar is equal to 0 and this x bar into 1 is x bar. So, that is x bar plus 1. So, x bar plus 0. So, that is equal to x bar. So, that is the second one. Now, x XOR x. So, x XOR x is, so x dot x bar plus x bar dot x. So, x dot x bar is equal to 0. So, that is 0 plus 0 equal to 0. Okay. So, x XOR x equal to 0 and x XOR x bar is nothing but x bar dot x bar plus x dot x. Okay. So, x bar dot x bar is equal to x bar and x dot x is equal to x, and now x plus x bar is equal to 1. So, this is the fourth identity, x plus x bar equal to 1. So, these are some identities that involve XOR operation, and this XOR operation is commutative, like this x XOR y is same as y XOR x. So, that is true for any other Boolean function also, and it is also associative, like if you have to do an XOR of 3 variables x, y and w, x, y and w. So, this property what it tells is that you can either do this XOR first and then with that result you XOR w. So, that may be one possibility, or you first do this y w XOR and then with that result you XOR x. So, both will give you the same result. So, this is associative in nature. So, these are some of the properties of this XOR gates that makes it interesting in various domains of communication systems, Boolean circuits and all, circuit design and all. Okay. So, XOR function implementation. So, if I have got say XOR AB is A B bar plus A bar B. So, if I do a straightforward implementation in terms of say AND OR gates. So, what I will do? I will have this A B bar. So, I will be taking this A and if this is the line A. So, I will take an inverter and this is the line B, I will take another inverter. So, I will get A bar here, B bar there, and now I have to do A B bar. So, A B bar means I have to take one AND gate where this A line has to be connected and this B bar line has to be connected, and then A bar B. So, A bar B, so this A bar line has to be connected and this B line has to be connected, and then they are to be ORed, okay, like this. So, as a result, number of gates needed is equal to 5, okay, 2 inverters, 2 input AND gates and 1 2 input OR gate. Okay. So, you can also do this by using these parts. So, they can be converted to NAND gates, each of them can be converted to NAND gates. So, as a result, so you can do the whole thing using 2 inverters and 3 NAND gates. Okay. So, that also can be done. However, there exists another clever implementation of this XOR function that includes only 4 NAND gates. Okay. So, we will see that. So, this is the 4 NAND gate realization of the XOR gate. So, we have got this. So, here this is basically X bar or Y bar, sorry. So, this point we are getting X bar or Y bar, at this point we are getting X bar or Y bar. So, which is nothing but X Y bar. So, this is also a NAND gate. So, here I am getting X Y bar and here it is NANDed with X, okay. And then, so we can say, so this is X dot X Y bar whole bar, okay. So, if we simplify, so you will get here as so X into X bar plus Y whole bar. So, you will get X Y bar. So, so you will get X Y bar from there. Similarly, from this side if you look into, so you will be getting here you will be getting this X Y bar dot Y whole bar. So, if you again simplify like that, so we will get this X bar plus Y bar into Y whole bar. So, you will get here X bar Y whole bar. Oh, sorry, I did a mistake here. So, this is X Y bar. So, ultimately the term that survives is X Y bar there and X bar Y here. Now, here this is another NAND gate. So, after this inversion, so this term is X Y bar and this term is X bar Y, and then I am doing an OR. So, I am getting this OR of these two. So, which is basically the XOR function. So, this way I can do this XOR realization, 2 input XOR gate realization using 4 NAND gates. Okay. So, that is safer, like we can save some gates, like in the previous implementation. So, we had here 2 inverters and 3 2 input NAND gates, but in the next implementation we have got only 4 NAND gates. So, we are saving some gates. So, this may be useful in some situation. So, just the opposite of XOR is XNOR. So, XNOR is known as the equality function. So, XOR was non-equality function, XNOR is equality function, and XNOR of AB is defined as AB plus A bar B bar. Okay. So, whenever both the inputs are equal, so if A and B both are equal to 1, then AB is equal to 1. If both of them are equal to 0, then A bar B bar is equal to 1. As a result, this XNOR function will be giving us 1 when either both A and B are equal to each other. So, we can see that XNOR of AB is the invert of XOR of AB. So, how do we prove it? So, this A XOR B, this XNOR is nothing but A XOR B whole bar. Okay. Now, this A XOR B is A bar B plus A bar B bar whole bar. So, this can be you can apply De Morgan's theorem. So, you get A bar B bar and A B bar. So, A bar B bar will give us A plus B bar, and this a b bar whole bar will give us a bar plus b. So, if you multiply, ultimately you get a b plus a bar b bar. So, so if you take the invert of XOR, so you come to a b plus a bar b bar, which is nothing but XNOR of a b. Okay. Now, if you just take one of the variables as a complemented one, so a XOR b bar, that will give us the XNOR of a and b. So, let us check that. So, let us say a XOR b bar. So, a XOR b bar, so it is given by a b bar bar. Just apply this x XOR y formula. So, it is x y bar plus x bar y. Okay. So, this x y bar I have written plus x bar y, fine. So, this is b double bar is nothing but simple b. So, a b plus a bar b bar. So, this is the XNOR. So, this a b bar a XOR b bar. So, this will give us this XNOR of a and b, and similarly by the similar logic, this a XOR a bar XOR b will also give us the XNOR of a and b. So, these are the relations between XOR and XNOR. So, this XOR is also known as odd function. So, why odd function? So, you see that if you take a 2 input XOR gate, then this is the logic expression. So, x XOR y is x bar y plus x y bar. So, if you take a 3 input XOR gate, 3 input XOR function x y x XOR y XOR z, then this if you expand, so you will get an expression like this x y bar z bar plus x bar y z bar plus x bar y bar z plus x y z. If you take a 4 input XOR function, then the expression will be like this. So, can we observe a pattern here? Of course, there is a pattern. So, in all of them, so the terms where odd number of inputs are equal to 1, it is surviving. Like for the 2 variables, so here you see that these 2 terms, they have got only one input equal to 1, that here only y equal to 1 or only x equal to 1. If you look into say this term, so here only x equal to 1, y and z are equal to 0. Similarly, in this term only y is equal to 1, x bar x and z are equal to 0. If you take a 4 variable term, this is x, y, z bar w. So, here one x, y and w, they must be equal to 1 and z must be equal to 0. So, whatever you do, so you see that here 3 variables should get the value 1 and one of them should get value 0. Similarly, here, so only x variable should get the value 1 and 3 of them should get value 0. So, either one variable is getting in a 4 variable XOR function, either only one of the input is equal to 1 or 3 of the inputs are equal to 1, then only output is equal to 1. So, in a general case, I can say that when odd number of inputs are equal to 1, then we will have the XOR gate output equal to 1. So, an n input XOR function is 1 by all minterms that have an odd number of ones in it. So, that is why XOR is also known as odd function, because it will have the odd number of ones equal to 1 in those minterms. Now, if we just look into the truth table, the Carnot map. So, this is for the 3 variables, so x, y and z. So, you see that they will be distributed like this. So, they do not group in a quad or pair or octet like that. So, they get distributed like this. Similarly, a 4 variable Carnot map. So, these ones are getting distributed in such a fashion that they do not form any pair. Okay. So, min terms are always distance 2 from each other. So, this is the property of odd function. So, you can realize these odd functions like this. So, this x XOR y coming here and x then z. So, x XOR y XOR z. So, we can realize by means of 2 XOR gates. If I have take 4 variable x, y, z and p, then this x and y can be XORed first, then z and p can be XORed and then this one can be XORed. And it does not matter in whatever order we do it. So, somebody may realize the same function like this also. Somebody may say that I will do this y and z XOR first, I will do this y and z XOR first and then I will XOR this output with the x. Okay. So, that is because of this associativity property of this XOR operation. So, it does not matter the order in which you do the XORing. So, these two are exactly same. Similarly, here also, so you can change the pair, like instead of taking y here, you can take p here, and instead of p you put the y here, that can be done. Okay. So, that will not change the expression at all, okay. It will remain all the same due to the associativity property of this XOR. So, we can also have something called an even function. So, even function, if we want to realize, so how can we do this, like complement of XOR, which is the XNOR. So, XNOR gives us the even function. Okay. So, many a times we use this XOR to generate the parity. So, whenever we have got an odd and even function, they can be used for implementing parity checking circuits in error detection and correction. So, what is parity? So, parity is something like this, that suppose you are you have got a communication system or where there is a transmitter and a receiver. So, this is the transmitter and this is the receiver. So, you are transmitting some bits from here to here. Now, suppose I transmitted the bit pattern 1110. Now, at the receiving end I should receive I should get this 1110, but due to this communication channel there some error may creep into the transfer. So, it may so happen that this 1 at the receiving end it has become 0. So, at the receiving end it receives 1100. Now, at the receiver side, how do we know that we have received a possibly correct pattern? Okay. So, for that what is done is, apart from these 4 bits that we are transmitting, so this 1110, this 1110, another bit is added. So, this bit is called parity. This bit is called parity. So, parity actually it keeps an watch on the number of ones that you have sent onto the bit stream. Like if we say that this parity, so we can say that whenever we transmit, we always transmit an even number of ones. So, that means in this case we are transmitting 3 ones, so that is odd number. So, this bit we make it 1. So, that at the receiving end, so if you receive a pattern like this, so assuming that this parity bit has been transmitted properly, so the received bit pattern is something like this. So, you have got 1100 and then parity bit is 1. But from this, if we calculate the parity bit, since we have taken the protocol that we will always be transmitting even number of ones. So, based on the received bit, so since these 2 bits are 1, this bit should actually is expected to be 0, but the receiver finds that it has received the bit 1. So, it understands that there must be something wrong in this transmission. So, receiver can detect the situation. Okay. So, this is called error detection. So, this is called error detection. So, the receiver can detect that there is some error in the transmission. So, this parity is actually used for this part. So, apart from the bits that you are transmitting, so you transmit the another extra bit. Now, you may follow even parity, where you check, where you make the number of ones even, or you can follow the other option, other alternative also. You can say it is odd parity, that is the total number of ones that you will transmit, you will make it odd. Okay. So, both of them can be done using this XOR gate. So, this parity generator, so this circuit generates the parity bits before transmitting, and this parity check. So, this circuit is present in the transmitter. So, this will generate the parity bit, and the receiver side we will have a parity checker circuit. So, it will check the parity after the bit pattern has been received. So, like this. So, suppose I have got this situation. So, even parity. So, I will make the number of ones transmitted as even. So, if it is the bits transmitted at 000, then the parity bit is also 0, because number of ones is equal to 0, that is even. If the message bits are 001, then the parity bit will be equal to 1. So, that number of ones in the whole message plus parity is even. Similarly, 010 also parity bit is 1, 011 the parity bit is 0. So, if you so this way for a 3-bit message, so we can write down what is the parity bit. So, P x y z, the parity must produce 1 for all input combination that contain an odd number of 1s. And whenever we get this statement, we understand that without doing any Boolean minimization anything, this statement straightway tells that this is an odd function. So, this is basically XOR of x, y and z. So, this parity so even parity generation can be done by means of the XOR gate. So, that is why XOR is a very popular gate in the communication system. So, how do you check the parity? So, you can do the operation like this. So, you can have a 4 input XOR circuit. So, you can have this, since you are getting 4 bit x, y, z and p, and if you do an XOR operation. So, if you get an 1, that means there is an error, because even parity means if you XOR with the parity bit also, you should always get a 0. So, if you get a 1, that means there is an error. So, for if you are on the other hand, if it is an odd parity, then if you are doing this, if you can use a 4 input XNOR gate, and so in this case if you get a 1, that means it is alright. So, if it is 0, then there is a problem. So, this way using this XOR and OR gate, so we can use this even parity checking. So, for even parity checking, either you can use a 4 input XOR gate, or in that case a 1 will indicate an error, or you can use a 4 input XNOR gate. In that case the output 1 will indicate that it is correct, 0 will indicate that there is a problem. Okay, so, you can also use the similarly you can also take care of the odd parities. Next, we will be looking into logic families like this different so far we are talking about logic gates and logic symbols. Now, it is the same logic gate. How do you realize? Like one implementation we have shown in terms of switches and lamps at the very beginning of this discussion. Now, there are many circuit elements that can be utilized in like say diodes, transistors, etc., that can be utilized for realizing different for getting different circuits. For example, this DTL, so this stands for this diode transistor logic, and then sorry, this diode transistor logic. So, this consists of diodes and transistors. Then we have got TTL, which is transistor logic. So, here all transistors are used for getting the circuit, for getting these basic logic gates. Then there is a ECL logic. So, this is this is again another family. Then we have got NMOS, which is metal oxide semiconductor family, and this N stands for N channel metal oxide semiconductor. Then PMOS, P channel metal oxide semiconductor. Then CMOS is a complementary metal oxide semiconductor. So, this way there are many such logic families that has been used for developing this basic logic gates, realizing these basic logic gates over the years. So, DTL is one of the first logic families that we had involving diodes and transistors. TTL came after that, and at present, so we are working with the CMOS family. Okay, this CMOS family is the most popular now because of several reasons, because of its compactness, because of its power consumption, less power consumption and all. So, this CMOS is going to be right now it is the de facto standard that we have for this integrated circuit chips. Okay. So, we will look into this CMOS in detail in the successive lectures.